Okay, thank you all for coming. Today, I would like to talk to you about resource theories. I'll first start with a broad introduction to this framework. And then I'm thinking maybe I'll tell you a little bit about some recent work that I've been doing in this area, which concerns the resource theory of coherence. Okay, so let me share my screen to scribble some notes. Okay, I hope
looks all right. Yeah, we can see.
Cool, thanks. Yeah, so resource theories, they constitute like it's a broad framework, right? With what I would call sort of spiritual similarities. That is to say, there, different resource theories might be technically different from one another. They might not really fit into like, some really strict definition of similarity, like say categories or something, but they share a lot of features in spirit. So a resource theory consists of one, a set of free states, right? Okay, I neglected to mention this, but I'm talking here about sort of resource theories where, we are concerned with states and channels and so on. Basically, it's about objects in Hilbert spaces of quantum mechanical states. You can make resource theories for more general objects, like people have thought about, for example, ruler and what do you call a straight edge and compass constructions on a plane as a resource theory. You basically define a certain set of free operations, and then you can think of it as a resource theory. But here I'll be talking about resource theories where the objects are like states, channels, measurements, and so on, connected with quantum information theory. Okay, so we have a set of free states. Can call it this cursive F. So it consists of some density operators sigma that belong to this set of the space of bounded operators on some Hilbert space. And in fact, you can have resource theories where these objects can act on different Hilbert spaces. You can bring systems together, you can partial trace, and so on. So these states they don't have to act on the same space, right? And this set F is just sort of axiomatically defined to be free. And I'll, in a few minutes, I will come to what it means for something to be free, or why we would want to define states as free. Then there are a class of free operations. And you can, we can denote this by, say, O. And now, the most broad definition of a resource theory would be something where these operations O consist at least of channels. So let's call them E, with certain properties, which I will come to in a minute. But when I say channels, I mean completely positive trace preserving maps, right? Some resource theories might admit free operations that are more general than channels. For example, you could have trace non-increasing maps, right? Which means you have some sort of like probabilistic transformations instead of deterministic. You could have measurements, but in the broadest sense, to keep things simple, we can think of the class of free operations as some set of CPTP maps defined by certain conditions. Let's come to those conditions in a minute. And this is basically it. Now, there are some conditions sort of for self-consistency of a resource theory. So you need that free channels, or let me call them free operations, must map free states to free states, right? So I'll write it in words first. That is to say, for all channels E in this set O, it must hold that for all rho in F, or let me call it sigma to be consistent with, for all sigma in F, E acting on sigma should also be in F, right? So the free operations acting on the free states can't produce a non-free state. A second condition that not universal or like necessary for a resource theory to be consistent, but it is often true, and it is quite handy, is that any free state can be prepared by free operations. In other words, for all sigma in F, right? And basically for all states rho, let's say, which may or may not be in F, right? In F or otherwise, there exists some some E, some channel in the set of free operations such that it maps this arbitrary state to this sigma, So what we're saying here is that it doesn't matter what you start with. So this row can be arbitrary, it can be trivial, it can be free itself, whatever. There exists a free operation that can prepare sigma from row. And because this tends to be quite a universal feature of resource theories, there are very few resource theories that people have studied where this isn't true. I like to use this as sort of a definition of the free states. I like to define free states by those states that can be prepared using free operations from any given input. Right. So can be used to define this set F of free states. Okay. So these are the basic ingredients or features of a generic resource theory. Right. Any questions so far?
So far, okay, I think.
Okay, thanks.
Anybody else? Yep, thanks.
Yep. So I think now I will take some examples to motivate this definition and to illustrate it. And sort of the most popular example and something that allows a lot of nice pedagogical discussion is where it's the resource theory of entanglement. Right. So here, the set of free states is basically the set of all separable states. Right. So there is a certain bipartition that's axiomatically defined, and the free states are those that have a separable structure, right? Some probabilities. And what would be the free operations? Maybe at this point, I will open this up as a little, I mean, I hope there are some of you here that are not too familiar with resource theories, otherwise it is trivial. Does anybody want to volunteer like an answer to what could be the free operations here?
Yeah, we have LOCC in the chat.
LOCC, okay. So I'm sure you all know what LOCC is, but just to just for completeness, let me mention this. So LO refers to local operations, which means I prefer not to give you a technical definition of this because I could make a blunder in trying to make it technical, but operationally speaking, this is like saying, you know, there are two parties, Alice and Bob, and these partitions A and B are in possession of these two parties separately, and local operations basically means that Alice can do whatever they want in their lab. Bob can do whatever they want in their respective lab. And there is no way that Alice and Bob can contact one another or coordinate their actions, except if they plan in advance on what they're going to do separately. But so local operations, broadly speaking, they look like local channel EA, and so local channel EB, at least if you think of channels for the moment to keep things simple, right? Local, so LOCC, so what's CC? CC refers to classical communication. So now Alice and Bob can do a little more because they can coordinate some of their actions because they have classical communication between them, right? So using classical communication, they can, if you add this to LOCC, you get, so LO, you get something called LOCC, which can have channels of the form let me call it, yeah, EIA. No, sorry. Let me represent it as sort of a composition rather than a sum. So something like E1A tensor E1B. I'll make this N composed with ENA N minus 1, N minus 1, B, and so on. So roughly speaking, these EI for, I going from 1 to any number N, these are local, but then in between, Alice and Bob can make some classical communication between them, and then they can make the subsequent operations depend on outcomes that they had in previous rounds, and these don't have to be complete channels like trace preserving things. I've just sort of roughly written it in this way just to get the operational idea through. When we can make a more technical definition of it, but I would probably get it wrong. Okay, so that's LOCC channels, right? So, and why is this a good sort of set of free operations for the resource theory of entanglement? Because LOCC cannot create entangled states, right? Entanglement from this set of separable states, right?
Varun, and
yeah.
If you would take your other definition saying that, let's say, my entanglement-free operations should be able to create all separable states out of, I don't know, the identity.
Yep.
Can I do I need, for example, this classical communication? Could I do it with, like, is it always necessary? Is it really necessary to, for example, coordinate Alice and Bob with, I don't know, some measurement outcomes or something like this?
Yeah, I think so. I think we would need, so there is a subset of LOCC called LOSR, local operations and shared randomness, where this shared randomness is classical randomness.
Okay.
I think they would at least need that in order to prepare any state locally, any sort of separable state locally. If I'm not mistaken, just LO without even shared randomness wouldn't be enough. We'll talk about this. It's a good question.
And do you know some references that actually focus on LOCC, or what one can do and somehow study this in its own right? Because I always see it as the counterpart of entanglement, and everybody focuses on entanglement.
For sure. In fact, I think in a way, people are much more interested in LOCC operationally than about entanglement as like this just abstract feature of states. There are reviews on the resource theory of entanglement.
Okay.
Sorry, I should have come more prepared for this, because this
No.
is not a great example coming from me, because I'm certainly not like as aware of entanglement theory as others might be. But if anybody else in the audience can point us to reviews or something, that'd be great. Thanks.
Yeah, I can also try to add it later to the email or as a link. Yeah. But if somebody has some recommendation, I would be interested. If anybody has some questions or something, sorry for.
I mean, I'm a little bit curious if you could just give a brief example how, I mean, I do believe it, and I think I remember something, but how you can generate any free, like any separable state through LOCC.
Okay, sure. Yeah. So in fact, yeah, so local operations and shared randomness should be enough. Let's try that. So say we want to create Pi sigma I A sigma I B. No, I should probably call this tau on B or something to sort of make it then so under LOSR we can assume that Alice and Bob pre-share classical randomness, right? So the with any of this stuff, whenever we say can LOCC do this, can LOSR do this, we're assuming that before the operation is, before the whole protocol begins, Alice and Bob can first meet and sort of discuss a sort of strategy beforehand, and they know what their task is going to be, right? So if they can strategize beforehand, they can arrange to pre-share, then they can share this source of classical randomness. Right. Sorry, this was a random stroke that I didn't mean for it to be. Yeah. So they can pre-share this classical information, and then go to their respective labs and just and then thereafter apply local channels, EA and I don't know, I don't want to call it F, but whatever, lambda B, such that, you know, these I get mapped to the right states, right? And how I did I write there on top? Okay. Okay. Yeah. So basically, they can just and such channels exist because they can choose these I's to be mutually orthogonal. So you know, no matter what states they have to prepare, they can find a local channel that does it. So all they need is a shared classical source of randomness. And if they have LOCC, they can basically use one round of some rounds of classical communication in the beginning to prepare this source of shared classical randomness. Right. So.
And so in that case, it's completely irrelevant what state they are supposed to apply it to.
Exactly. Yeah, yeah. They can resolve to ignore the input they have and yeah, prepare these fresh.
I see. I see. And so the statement is that classical randomness so means that you have essentially this access to this tensor product, I mean, to this state that you described there. Is that
right? Right. So these are like, in a sense, maximally correlated random classical random variables. Right?
Yes, I see.
Or, I mean, correlated in any way they please. But for example, it can be maximally correlated, in which case they can do whatever. Yeah.
But purely classical correlated. So essentially, I mean, yeah, I see. So it's essentially in the definition of LOSR, it's already included to say that you essentially have access to how would I call that?
Incoherent separable states, no?
Well, I would call it, it's essentially already a density operator that
yeah, you can make it a sort of tight
kind of the right structure. I see, but not fully yet, because sure, if you then apply the channels, you go from a pure state to an arbitrary mixed state in the system. I see. Okay.
I think if I'm not mistaken, these so LOSR would be like saying it is LO, but starting with an arbitrary initial state that doesn't have discord between A and B, right? So.
And Varun, can you say if I have the somehow maximally correlated states, are there some simple operations so that I can transform those classical probability vectors into each other?
That's a great question. And that brings me to like more familiar grounds for me, which I will cover in a bit of detail later. Yeah, thanks.
But then purely
yes, there do. Yeah, the short answer is yes.
And can you just say again what you said with discord? If I remember correctly, if you have zero discord, then essentially you don't have any quantum correlations. Like your mutual information would be purely classical somehow.
Yeah.
No? And the state that you described here, that would be one without quantum discord.
Is LO plus initial discordless states. Sorry, you were saying something in the end there. Yeah.
So I just try to understand, because I actually have never computed Discord for specific state. Are you saying that the state that you wrote there, this sum over PI, II, A, II, that's exactly of such a type?
Yes, I'm sure that this has zero discord.
I see. And a general separable state, can that have discord? No.
Yes, for sure. So yeah, so these will not be all separable states. There are separable states that do have discord. Off the top of my head, I am unsure whether this structure I wrote down here is basically essentially all of the zero discord states. But I think that is true. I think it is true that zero discord means that you should be able to express a state in this form.
Okay, now, I mean, maybe it takes us a bit too far, but I actually don't remember all these things. So you're saying we have a distinction between classical correlation, quantum correlations, and entanglement, and they can all appear. So a state here with a separable state with quantum discord has quantum correlation, but no quantum entanglement.
That is true. Yeah.
And can you just explain briefly what? So
sure. So here's
I always thought quantum correlations are the correlations that cannot be classically explained, and then in some sense entanglement is also closely related to quantum correlations that cannot be classically explained. I mean, of course, it's also related to violating Bell's inequalities and so on. But yeah, I'm very curious if you could clarify briefly, maybe.
Sure. Yeah. So here's an example of a separable state with discord, right? So if you had, just say, a half and half mixture of 0, 0, 0, 0 plus 0, 0 plus plus. I'm pretty sure that this state would have, 1, 1 or something here. Yeah, I should make it non-trivial. And plus plus, right? I'm pretty sure this would have discord in it, even though it has no entanglement. So it is separable. So sorry, here when I wrote this structure, I meant that there must be some local bases I, and let's say I tilde, right? They don't have to be the same bases, obviously. But using some local unitaries, you should be able to bring the state to this form. And yeah, so this is a state that with just local operations, you couldn't bring to this form of shared classical randomness, right? And it's good that you mentioned this. I mean, this is turning out to be a bit of a digression, but I think it's a good one because you also mentioned non-locality. So it turns out that there is a whole lot of hierarchy of correlations, right? So we have the product states. Which have zero correlations. You can say that within the product states, there are, classical joint classical distributions, joint, but sort of, uncorrelated classical distributions. Right?
Well, but that requires a special choice of bases, no? But product states is a basis independent statement, which states are somehow classical within this Hilbert space that requires some preferred observables or preferred bases, no?
Actually, no. That's the great thing about the definition of entanglement and separability, that separability or entanglement is partition dependent, for sure.
Yeah. I mean, with separability and entanglement, I agree. I'm talking about the little ball that you drew inside the product states.
Right. So the little thing of uncorrelated classical distributions, what I mean here is that essentially the little thing here, you can think of it as equivalence classes of quantum states, where each equivalence class corresponds to one classical distribution, right? So if you have some classical distributions, PA tensor QB, you can say that essentially any...
So for a system of 2 spin 1/2 particles, I know what the product states are with respect to this decomposition, but what are the what's the little thing?
So you can say that basically any bipartite quantum state that has this form for some classical distributions P and Q, you can think of it as being practically no more or no less than just having the classical distribution, right? Because as far as the operational difficulty of non-local operations is concerned, like if you're able to do things locally, but somehow restricted to what you can do globally on AB, then the distinction between this and this is not very bad, right? It's essentially the same thing in terms of local operations. So you have these product states and just product classical distributions. I'll put this somewhere on the side, maybe if we need it later.
So here you define the small box now, with those independent distributions.
Yeah.
And so the idea is that you could write the stuff, you could write it out in the separable way, but then there's a way of simplifying it. So
yeah, and I should just to get across the idea that these are not going to be convex sets, right? If you mix things, if you mix product things, you won't get other product things.
Okay, but I still didn't completely get the equation that you wrote there. The left-hand side are product states, no? I mean, that's your definition of product states.
The left-hand side, you can, I should just put it.
Cartesian product.
Yeah, there's just a classical, just uncorrelated.
Actually, independent classical distributions, right?
Yeah, independent, that's a good word. Independent.
That's the idea, right?
Yeah. Distributions. So joint distributions on A and B that are uncorrelated classically.
Oh, and you're saying that can be with respect to any.
Indeed.
So with respect to any orthonormal basis of HA and HB.
Exactly.
So the small box is like tensor rank 1, separable states with tensor rank 1, right? You can compress it onto a single box.
Yeah. Exactly. And so then,
but I'm still confused because the right-hand side just says a tensor product of a general density operator, tensor product with another density general density operator. So I don't know. I don't see what product state is there that cannot be written like what is written to the right side of this equation.
Yeah, that's a good point. Yeah. Yeah, I think that's a really good point. And in this sense, really there would be no distinction between these sets. Okay, the reason that I drew this.
My interpretation would be that there is a difference, provided that in the Hilbert spaces HA and HB, you have a preferred basis I and J.
That's
and
true.
Then, of course, only probability distributions with respect to this preferred basis lead to the substate of states that can be written in this language, namely essentially those product states that are product states of density operators that are diagonal in the preferred basis.
Right.
So that was my point at the beginning, that I had the feeling that this sub-blurb that you drew may be basis dependent, or if it's not basis dependent, then it's identical to the big blob.
That's true. Yeah, that's a good point.
Okay, then we
so
clarify.
Let's make this like product with respect to product with respect to some local bases I and J, right? And then you can complete these to their respective convex sets, convex closures. So when you complete the product states to its convex closure, it produces this what I call F set, but I mean in the literature it's just called set, right? The set of separable states. Now, each of these things that are product in a certain basis would produce its respective convex hull. And then if you took the union of all of those, let's say some I tilde, J tilde, and so on, you took the union of all of those, you would get essentially the set without discord, right? No discord. So that's the reason that I wanted to mention this classical distribution thing. So I will now get rid of this mess here. I'll just say there's a convex set of separable quantum states. As a subset, it contains things which have zero discord. And again, the set of zero discord states is not convex exactly because of this basis dependence thing, right? That you mentioned, that this zero discord thing consists of the union of all possible convex combinations within specified bases. And then you have the set of just product states, which is again non-convex.
And they intersect somehow?
Yes, they intersect. Yeah.
And they're product states that have non-zero discord, or product states is a subset of?
Yeah, this would be a subset. Sorry. Yeah.
Yeah. Okay. Good.
Okay. Yeah. Product. Yeah. Good point. Yeah. So you have product states, separable states.
Okay. And you're saying zero discord, that's not basis dependent, but
it is not.
It is the union of certain types of states that can be essentially that this are described by classical distributions over.
Right. So if you take convex completions of these basis dependent sets, you get certain sets, convex sets, and you take the union of those convex sets, you get all of the zero discord states.
Okay. And you gave this example on top.
Yeah.
That had zero discord.
Yeah.
But was not a product state, but it was a separable state. So all zero discord states are separable. Yeah.
Yes, all zero discord states are separable, but this is a non-zero discord separable state. Yeah.
Okay, I really appreciate it. Thank you very much for
So
clarifying.
I think, if I'm not mistaken, zero discord is equivalent to there being an eigenbasis that consists of product vectors for the given state. But I will leave that as a thing to look up later. I won't commit to that. Okay, so we have the separable states. And somewhere out there, we have entangled states. So anything outside of separable states, right? So if this is like this bounding curve is for all states, acting on some bipartition A and B, anything that's outside of the set of separable states is entangled. But already there are interesting things going on within the set of separable states. And now within entangled states, again, there's a hierarchy of different types of correlations. So there is a subset of the entangled states that is PPT, positive partial transpose, right? So if you take the rho AB and you apply transpose on the A part, and if this remains a positive definite object, then rho AB is positive partial transpose. And it turns out that even though the transpose is a basis dependent map, whether a state is PPT or not is basis independent, right? And there are entangled states that are PPT. However, if the partial transpose is not positive definite, then rho AB is entangled. So having a non-positive partial transpose is a sufficient condition for entanglement, but it's not necessary.
So that's where, for example, logarithmic negativity would come in. So that would somehow discriminate.
Exactly. So there are the negativity
would essentially distinguish between PPT and outside of PPT.
Yeah. Measure of non-PPT-ness. Right. So in a sense, if you find non-zero negativity, then you certify entanglement. But if you find zero negativity, then it's inconclusive.
Yes, very good. Very good. I remember that.
And then there are there's PPT, and there's like states that they're Bell non-local. And actually, I'm not informed about the convex structure of these things and so on. I don't know if this is it's probably not going to be a convex set, right? So not all entangled states are Bell non-local. There are some that are Bell local, and stuff outside of it are non-local in the sense that there exist Bell tests that Bell inequalities that states outside of the Bell local state would violate.
But all PPT are Bell local.
I'm not sure about that actually. I don't know about the mutual sort of relationship between PPT and Bell Local, but
Okay.
something that I know is that it's related to a concept that I haven't yet discussed, but I will get to, is something called distillation, which roughly speaking is converting many copies of noisy resource so something like row n copies to typically fewer copies of good resource, right? So something like in the entanglement case, it would be like bell pair or something. And R is like some rate of distillation. So for every n copies of row, you get R times n copies of some nice thing like bell state. And the deal is that the technical definition of this sense of distillation, where you have like many copies and you take arbitrarily large n and so on, it's too much for now. But I will just mention that if rho AB is PPT, then the rate of distillation is 0. So if you have a PPT entangled state, then if you have many copies of such an entangled state, using just under LOCC, using just LOCC, you cannot distill nice entangled states at any non-zero rate, right? And it's an open question whether there are, so these states are called bound entangled. So all PPT states are bound entangled in the sense that they have 0 distillable entanglement, but it's an open question whether there are NPT bound entangled states. Okay, so you have here bound entangled states, and we don't know if there is a separation here. And then there are like Bell non-local states. There are other things in here like steering. I think steering is somewhere between Bell non-local and separable. So there's a whole bunch of different levels of correlation that bring a rich structure to this broad theory of entanglement. But what I wanted to get to next is, okay, we took LOCC to be this sort of axiomatic set of free operations, and it was almost like in a self-explanatory way, operationally meaningful. But actually, so LOCC, this set of free operations, it's operationally, let's say, meaningful or well-motivated. But technically intractable. So for example, here we looked at roughly how you could think of an LOCC, right? You could have one round of some local operation by Alice and Bob, and then some communication, and then the next round, where each round could be like, a trace non-preserving thing, right? So you could sort of have measurements in each round, and conditioned on the outcomes of measurement, you could adapt the operations of subsequent rounds and so on. And because LOCC just by definition allows an arbitrarily large number of rounds, really we're thinking of the closure of all of these things with arbitrarily large n, and that's that's a very ugly kind of beast to understand. So for this reason, there are other sets of free operations that are still free in the sense that they map separable states to separable states, right? So these include so-called, of course, we already looked at LOSR. So these are also valid sort of candidates for free operations because they don't take you out of the set of separable states if you start there. Then you have LOCC here. So I'm arranging this in a sense in increasing order of how powerful these sets are, right? So then there's something called PPT preserving, which are all channels that you can do on Alice and Bob that that may take some separable states to entangled states, but they will not take any PPT state to a non-PPT state, right? So essentially, you're expanding the set of free states a little bit, just because if you consider PPT preserving, but also sort of the free states relaxed to PPT, then it turns out that a lot of questions that you can ask about LOCC are easier to answer for these things because PPT is a positive semi-definite constraint. So it's amenable to semi-definite programming. Then there's something called the separable operations, which is just defined as the maximal set of channels that map, I'll call it F set to distinguish it from operations So if you define sort of the you have your set of free states, the separable states, and you just define the set of all possible channels that would map separable states to separable states. That defines this class of, no, I think I'm, so there's separability preserving, set preserving. So I think there are subtle distinctions between PPT channels and PPT preserving, separable channels and separability preserving, and so on, which I'm not very familiar with. So I'll just say there's this largest possible class of sensible operations, which is like they preserve the set of separable states. And this, for example, would include the swap between Alice and Bob, right? So includes swap AB. But clearly the swap of Alice's system with Bob's system should be a really non-local type of thing to do. So in that sense, it's operationally clearly much more powerful than LOCC. Nevertheless, it preserves the set of free states, and it's easier to get results about this. And so people use things like PPT preserving, separability preserving, LOSR to get upper and lower bounds on things related to LOCC. Okay. Are there any questions at this point? Okay. I think so. Marek, what do you suggest for like how long we should take this?
Yeah, I'm on that train. Sorry.
Okay.
I'm on my.
Yeah. Maybe I will. I can say something for another 25 minutes-ish until 6 p.m. Singapore time, just to go a little bit beyond the example of entanglement theory.
Yeah, I think that sounds good.
Okay, cool.
So you only wanted to speak for one session, or you would continue next time? I don't remember.
So I have been scheduled for some session in March, so I'll be happy to sort of continue then. So I was planning to then talk about something more specific, like something related to my recent work. But today was meant to be a broader introduction to resource theories.
So for me, it's very useful. Thanks so far.
Okay, cool. Thanks. Yeah, so I can, so what I'll do is for another half an hour or so, I'll just talk about, again, things that are not very specific to any resource theory in particular, but quite useful tools in general. So
I mean, so far you don't really, you didn't really define why it's called resource theory. You know, it somehow, if I remember correctly from seeing that before, the point is somehow that you have these free operations and they somehow don't change the resource, but then you have operations that increase or decrease the resource, and you only have somehow like you don't really have a measure. I mean, you don't have an ordered set. No, like I mean, I guess for entanglement of pure states, you have the von Neumann entanglement entropy that somehow puts puts an order on it. But as soon as you even go to mixed states for entanglement, you don't have an ordering by a single number. But you still have somehow, you still have, what is it called, some partial ordering, or what's
exactly. So a resource theory, so I'll just say RT, has a partial ordering among states, right? So you can say rho let's use this triangle symbol to sigma if, or you can just say, if there exists some channel in O that maps rho to sigma, right? So just the condition of whether there being a channel in the set of free operations that maps a state to another state defines a partial ordering among the states. And then the sort of the ultimate answer to most resource theoretic questions would be to be able to come up with a simple, like easily computable condition for when rho can be converted to sigma. Like if you can come up with that kind of condition, then essentially most things that are interesting or like useful, you can answer using that. But that's usually not so easy. So what we do is we use resource monotones. A function f from states to the real numbers, such that sorry for my poor handwriting, such that this necessarily implies that f of rho is no smaller than f of sigma, right? So some kind of real valued function that would respect the ordering, the partial ordering defined by convertibility, convertibility relation.
I see, but here essentially the monotone only provides you the information if f of rho is not larger than f of sigma, then you know that it cannot be generated by a free. But if it is, you still don't know if you can generate one from the other.
Yeah. So the more monotones that are sort of easy to compute that we can find and that have like sort of information that's as different from one another, the closer we come to learning about the exact nature of this partial order. So in some special cases, we end up being able to find a finite number of monotones that are complete, in the sense that they completely determine the partial order. And that's what I would like to talk about. So some nice resource theories, right, that in a sense that are gentle enough on us that they admit a finite set of conditions or monotones that completely determine the convertibility conditions. So one example would be entanglement on bipartite pure states. So if you have, just two parties, A and B, something I didn't mention here is that, of course, you can have all of the same stuff, but with like more than two parties, and it becomes more complicated, of course. Okay, so if you have just two parties and you consider only pure states, right? So if you have some psi AB, so first of all, it turns out that any pure psi AB can be expressed as square root pi IA tensor with orthonormal. So any pure bipartite state has something called the Schmidt decomposition. Where you can always find local orthonormal vectors on A and B, such that you can express the state as a linear combination in this way. You can express the vector corresponding to the state in this way. So, and that's really handy because it turns out that if you have two pure states, so this vector P is called the vector of Schmidt coefficients. Schmidt coefficients of psi. So if you have psi, and you're interested in whether there is an LOCC channel that deterministically takes it to some phi, then it turns out that this is equivalent to the condition that this Schmidt coefficient of psi is majorized by the Schmidt vectors for phi. I will tell you in a minute what I mean by this symbol. So it is called the majorization relation. So it is a relation between classical distributions, right? Because for normalized pure states, these P's and Q's are going to be classical normalized distributions. So it is a relation between normalized distributions and P. So define P with a down arrow as, oh, sorry, it should be in order. P max, P second, no, yeah. So some, okay, I'll just informally define it, some permuted version of the original vector such that you know, right? So you've rearranged the components of P in non-increasing order. And so then P is majorized by Q if for all I in so between 1 and n, some or I would say k, some I going from 1 to k of P so this means that the first component, the largest component of P has to be smaller than the largest component of Q, right? And the two second largest components, their sum should be smaller than the sum of the two largest components of Q, and so on, right? And of course, the sum of all of them is just going to be equal. So because they're both normalized distributions. Okay, so in short, there exists an LOCC channel that can deterministically map a given pure state to another given pure state if the vectors of their Schmidt coefficients obey the majorization relation. So this is something that comes from Nielsen. It's called Nielsen's theorem. Right. And this is it's so powerful that like as soon as you have majorization involved in in some at least some part of a resource theory, like here we have entanglement theory, but only for the pure states the condition is given by majorization, but that opens up a whole lot of powerful tools that are related to majorization that you can then bring to bear on problems in the resource theory, even outside of just the pure state case. This includes so-called catalysis, where the question is whether I will talk about catalysis in a future session, but just informally, catalysis is something where if there is no free operation, but there exists some third state tau such that rho tensor tau can be taken by a free operation to sigma tensor tau, right? So you can add another state tau, and there exists a free operation that takes you from rho tensor tau to sigma tensor tau, so that you haven't changed the state of this additional system. So you call this a catalyst, right? And in the future, maybe I'll talk about catalysis in resource theories, but because somehow entanglement can be related to majorization, a lot of known results about majorization, including stuff about catalytic majorization, can be imported to learn about corresponding things in entanglement theory, right? And there are other resource theories where majorization determines, convertibility. So this includes so-called noisy operations, where the resource is purity. So you can say that the resource is purity, so that the set of free states are only of the form maximally mixed states of the dimensionality of whichever system, right? So you're not even allowed to just embed a given state in a larger Hilbert space. The only free free isometries are unitaries and just unitaries, right? Just stuff that doesn't that can't embed the given state in larger systems. So a generic noisy operation looks like you take rho and you map it to, so let's say rho A, you map it to okay. Unitary. So some unitary channel, right? So you just take the state you had initially, you attach an ancillary system B prepared in its maximally mixed state, apply some unitary on the space of A, B, and then partial trace over an arbitrary subsystem of your choice. It doesn't have to be A or B or anything, it could be any subsystem. So this this class of operations is called noisy operations. Noisy operations, roughly speaking, they only increase the entropy, right? They increase any measure of impurity or mixedness. They only decrease the purity of states. And it turns out that rho can be taken to sigma using noisy operations if and only if the eigenvalues of rho majorize the eigenvalues of sigma, right? The vector of eigenvalues. Note that in the case of so when majorization featured in the theory of pure state entanglement, the majorization relation went the other way. So, we needed the Schmidt coefficient, the Schmidt vector of rho, to be majorized by the Schmidt vector of sigma. or phi in that case. Whereas in this case, in the case of noisy operations, rho, the spectrum of rho needs to majorize the spectrum of sigma in order for there to be a noisy operation taking rho to sigma. Then there are other examples. Resource theory of, or I will say resource theories of coherence, which will be the sort of more specific topic that I plan to talk about in March. So here the free states are, the convex, essentially mixtures of some canonical basis, classical basis, right? So this is also related to the earlier discussion of there being some preferred basis. So if you define a certain preferred classical basis and say that states that are diagonal in that basis are free and everything else is a resource, you can come up with various definitions for the free operations, that different free operations result in different specific resource theories of coherence. And it turns out that in more than one of these resource theories of coherence, free states, free state convertibility is again governed by majorization, this relation, right? And it's very similar to how majorization behaves or like figures in entanglement theory, because it's essentially the same kind of linear algebra that's playing a role. So hopefully I'll talk in more detail about majorization and the resource theory of coherence in the future. I think with that, I should close this session. Yeah, please let me know if you have questions.
Yeah, really, thank you very much for this overview.
Thank you. Yeah, thanks for all of the questions and discussion as well.
Yeah, thank you so much. That was really interesting. I had a quick question, if that's okay.
Yeah, please.
So you were chatting before about how like separability preserving operations are like operationally more powerful than LOCC, and an example is like the swap operation. Yeah. I was wondering if you know much more about like other things that separability preserving operations can do beyond LOCC, like.
Yeah, I think, for example, they can increase the Schmidt rank of pure states, like this thing that I discussed. So if you have two pure states under LOCC, you can only go from something of a certain Schmidt rank, where rank means the number of non-zero Schmidt coefficients, to something of no larger Schmidt rank, because that's a necessary condition for majorization. Turns out that with separability preserving operations, you can increase the Schmidt rank. And I guess that has operational consequences, like you might be able to do better at certain tasks with just with SEP than with LOCC.
Right, cool. Oh, thanks.
Yeah, and there's a broader question, I guess, that did come up earlier about why we would even call something a resource. And for example, in the case of entanglement, It is a resource because you can do things like teleportation, where what you're doing is you're using a static resource, namely an entangled state, and converting it into a dynamical resource, namely a classical, a quantum channel, right? There is super dense coding where you're taking the static resource of an entangled state, converting it into taking this entangled state and a classical channel and converting that combination into a classical channel with a larger capacity of communication. So there are such like operational advantages to having these resources, and that's the reason that people are interested in systematizing their study. Yeah. Thanks. Any other questions? Okay. So at this point, I will stop the recording.